You have, this one was supposed to take like 20 minutes, they said, but I think we could do this one a little bit faster, especially with what we know about magnetic fields and things like that. So you got a particle that's entering into a region of a field, and it's positive. And so the first couple things to kind of get out of the way is that just making sure we note that this is a positive particle. And I was practicing this with AP1, just kind of like critical reading skills when we're going through, picking out the major ideas that we want to pay attention to so we don't miss something. And in this, you're supposed to be represented with an electric field that's drawn toward the bottom of the page. So the first thing we got to recall is which way electric field lines are drawn, and it's always in the direction from what a positive test charge would feel. And so electric field pointing down the page, when this positive particle gets in there, it's going to take a path that would feel a constant, steady net force of electricity down on it. And so the path there is going to be a parabola. So you should have drawn a parabolic path. It doesn't necessarily matter if you exited in, let me kind of, they have a pointer feature now in Notability, which is kind of nice when you're presenting. So it could have exited like here or down here. It didn't really matter on the rubric. Now I drew the electric field lines in. On the answer, it doesn't have you draw them. I would be careful not to draw anything that's like extra because they didn't indicate to draw the electric field lines. So yes, that helps me visualize it, but I don't know that they would have taken off or not according to the rubric, but you should have just drawn the dotted parabola. David, good to see you. How is the, David's chiming in with Interstellar, also my favorite movie. How was the biology test? They tried to do it online. I'd like to get some feedback on that. So I'll keep going though. So on the figure below, draw what would happen in a magnetic field. So if the magnetic field was pointing down the page, or sorry, out of the page, again, critical reading, magnetic field is out of the page, then what you'd have in here would be little dots. And if they have little dots, according to your hand rule, have those coming out towards you. Your thumb would be directed, I guess, to the right. Hopefully this is all showing up correctly on the camera. I don't know if this is reversed. My brain can't think that hard. Anyway, and then that would force this thing down the page. The only difference is as it forces it down the page, it's not a steady force always downward like in this first scenario. Because what you'd have happen, I gotta turn off notification. Oh, it is. Oh well, if you're okay with seeing it blip in every once in a while, I'm still getting notifications in. So David said the test went well. Okay, well, on that magnetic field then, coming out of the page, you're gonna be forced downward initially. So like right here, the force would be downward, but then that would start to change because then the trajectory of this thing is gonna be curved, more like in a circular path. And instead of the force always pointing down, let's actually change this now. Let's see. Sorry, bear with me here. We're going to change the settings because I'm noticing that this is kind of annoying to have it chime in all the time. We're going to turn off notifications on that. What else? Probably Google Classroom. Okay. Let's get back to physics. All right. So the main idea that I'm trying to get across is that you have a continuously changing for B field. You cause a continuously changing force direction. And it would always be directed 90 degrees to the velocity. So if your velocity was this way, then the force would be this way. Then your velocity would turn this way, then your force would be this way, then it would turn this way. So it kind of looks the same as far as like the pattern, but that in part 2, this one here, this one is, I got to get used to this. Part 2 is circular, and this one's parabolic. All right, so then on part 3, which of these would be like what Earth's gravity would do near the surface? In that case, we're going to be more like in the electric field, because we want the force to always be downward. If this was gravitational field lines, this one up here would mimic that same idea. And they wanted you to write that as a paragraph. Let me show you the rubric real quick for that. So far, get it pulled up side by side. In this rubric, where is it? Okay. So on that third question, you get 1 point. It's only worth 1 point to just say, for indicating the motion, the electric field is more similar to a projectile because it is parabolic and it's always, the force is always downward. So there wasn't a lot as far as what you had to write on that. You should really only be writing a paragraph if it's like, if they say write a paragraph length response. So keep that in mind. Okay, so on to the next part. Now we got this proton beam, and you get some particles that are swinging up this way and coming out at 1, and then you get some particles that are swinging that way and coming out at 2. And at first this seems like it shouldn't work because you know, protons should always be curved the same way, but it totally depends on the force in each direction. So this is where I would ask you normally, like, which force is pointing upward, which force is pointing downward, but then I have to wait 30 seconds for you to chime in. So instead, I'm just going to keep going. Oh, well, that's nice. Now we're making fun of Harrison, apparently, through social bullying at a distance. Be nice to each other. Okay, here we go. So if you're talking about the force of magnetism, that would be downward. The electric force would be pointed upward. And so depending on how big these arrows are relative to each other, right? If this arrow increased in size, well, then that particle is going to swing more towards like position 1 because it's going to accelerate more. If that force was smaller, then it's going to be having a net force downward and it's going to come out at position 2. So your paragraph length response, this is the one where we actually have to kind of back it up with physics principles and write it a little bit more. But I just want to show you that rubric that you would have had and see kind of how you did as far as getting points. So I will let you read through that rubric and see how you did on your own while I go get some coffee real quick. 2 seconds. By the way, the kitchen color is going to stay for at least, I don't know, through this year. I told my wife all of your great feedback on the kitchen color, and now she's embarrassed and she's like, well, stop filming in there. I said, well, half of them liked it. So I don't know. For now, we're going to keep the same color. All right. So make sure when you're kind of reading through that rubric, there was one part in here I thought that was interesting, that you get 1 point. Let's go down to here. So for a logical, relevant, and internally consistent argument that addresses the question and asks and follows the guidelines described in the published requirements. So basically, you get a point, a freebie point, as long as you can write a paragraph, is pretty much what this is saying. So if you follow the rules for writing a paragraph length response, which you should have hopefully read through in your 5 steps to a 5, you can get one of the 4 points, or sorry, one of the 5 points allotted for this question. So just practice that as we're gonna do more of these in the next few days. Just make sure we're doing that. Oh, there we go. Harrison's in, and he likes Major League. That's a good movie too. All right. I wish this was more like automatic. And maybe we could switch to this with such a small group. Let's see how many are in here. 1, 2, 3, 4, 5, 6, 7. For you guys, for AP2, I might just switch to doing like real video meetings, just so it's a little bit more interactive. But yeah, with AP1, I got 120 students, and that's not possible. So anyway, you'll give me feedback, I'm sure, after we're done with this. So moving on, if you have any questions about your rubric, like if you say like, hey, I wrote this, will this give me credit? Or I'm not sure how they would have wrote that, please jot it down and I'll go back to it. But for now, I'm going to move on to what I consider the more challenging question, which was the circuit problem. All right. First thing we have to know is that this symbol, notability, come on. This symbol here is the power supply. That little arrow through it, that is how you note a power supply. And we haven't used that notation, but I think it's worth mentioning. Then, as you start to set this up, they're purposely graphing this backwards of what we would have done in class. Like most students or most physics classes are going to be doing a, what do you call it? Like a voltage versus current graph as a Ohm's law lab. And they're specifically writing a current versus voltage graph just to flip this so that you have to interpret that slope a little bit differently. So as we start to set that up, it says, it's an ideal variable power supply and ohmic resistance of R. And so now we got to kind of pay attention that there's two different R's here. You got this capital R and then this lowercase r. And that lowercase r, just saying it's just acting like another resistor hooked up in the circuit. So yeah, they say it's internal resistance, but it really doesn't matter. You would just treat it like another resistor in your circuit. From there, we need to sketch a possible graph for circuit 1. So for circuit 1, you just have an amp meter with no resistance and just a single resistor. So if you graph current versus voltage, we should see a direct relationship, and you would just get a graph something like this. Okay, so actually, let me color code this just so we're keeping it consistent. And then for circuit 2, because you have that extra resistor in there, then that is going to cut down the overall amount of current coming out of the battery. Think about as you add more resistors in series, it's going to increase overall resistance, which is going to draw less current out of the battery. And so anything like that, as long as the slope of 1 is steeper than the slope of 2, that would get you credit. And as far as how much credit they awarded, let's go over to this. So 1 point for graphing a straight line with a positive slope through the origin, and a second point for a straight line with a positive slope through the origin with a smaller slope. So I didn't really think about it, but that is important that we need to have them go through the origin. With the 0 voltage, there should be 0 current. So that's how they're going to break up that scoring guide. Also feedback. You guys are kind of my first group that I'm troubleshooting this with. I know the screens, I don't know. I'm trying to do this. If I could show you my setup here, it's a little obnoxious. I have like computer, iPad, phone, because the phone's camera is way better than our school's laptop camera. And then I got this external mic. If you could just give me feedback on if you can hear me fine with this external mic. Also, if like the screen when I'm doing this, if that's too, like, would you be able to see that whole document the way it is now, or do I need to be zooming in like this on each thing that I'm talking about for you to be able to read it clearly? So that's stuff I'm just kind of curious of how this looks, and you can leave me a comment in there as we go. All right, next. I'm going to pull up a little bit of space to write with. So workspace. Okay, So on this one, in part C, explain how your equations in part B account for any differences in the graphs between 1 and 2. So your equations, did we write the equations? Sorry, going back. When we write the equations, for circuit 1, it's as simple as the current So it doesn't say you have to write them in terms of like the graph up above. So you could write them like that. But really what we're saying is that the sum of the voltages equals 0 around the circuit. And so if you said the delta V of the power supply minus the, in circuit 1, it looks like it's just that single resistor. So how would you write a voltage of a single resistor? You could write out V of capital R, but you notice the variables that I get to use, I can't write minus voltage of that. So instead, I have to write it in terms of I and R, which is a voltage. So delta VPS minus the current coming out of the battery times R should all sum to 0. So pretty straightforward for that first one. That is a conservation of energy idea. That's Kirchhoff's loop rule, that the total voltage, as you add them up in a single ring, should always add up to 0. Well, you do the same idea in the other one. Start with that voltage of the power supply. And if you start subtracting out the resistors as you go, you would say, back to the circuit, it's technically like I times little r and I times big R. But instead of writing those out individually, you could just say I, factor that out, R plus big R. All of that should equal 0. So that is your two equations for writing the energy conservation. I think that one's a little tricky because like if I read that at first and then they're just talking about energy, I'd probably be looking at the toolkit and not recognizing that all this is just a loop rule. So this is, I guess I want to bring up a point that loop rule is conservation of energy at its foundation. Like that's kind of what the point of that statement is, and that loop rule depends on that. What the junction rule, if they don't ask in this one, but if they do ask about junction rule is more about conservation of charge / matter. So meaning like if I have 2 gallons coming into a junction and it splits 1 gallon, then that would be conservation of matter. Well, thank you, Nate. Nate gave me feedback. The rest of you probably left and are not watching anymore, so that makes me sad, but I'll just keep talking as if you are. That's another thing I haven't thought of, is like there's no way for me to indicate or know who's actually still here. So I could just be talking to myself for a while, and I'm okay with that. I need to talk to someone. I'm going crazy. So, all right, let's move on. On part C, you explain how your equations in part B account for any differences between the graphs in part 1 and 2. And in part C, it's actually, this might be easier, just pull up the rubric, but you just want to talk about how your slope of that graph is actually the inverse of resistance. It's proportional to the inverse of resistance. If you have voltage, right, if you had voltage versus current, your slope would be resistance in this y equals m times x. So you switched it. You have I equals 1 over r times voltage. And so your slope is actually, okay, I'm getting your feedback that you're still here. That's nice. It is a little weird that 30 seconds later, then I know that you're here. But anyway, we'll keep going. I just won't give up in 30 seconds. How about that? All right. So this is how you'd want to get through this, is that the slope of your graph is the slope of your graph is proportional to 1 over r. And so as the resistance goes up, like in that second, let's do this one here, in current circuit 2, this overall resistance is higher, and therefore the current is smaller. So you see that on the graph, you get less current, right? If you trace that across, less current given the same voltage. This graph would be like over here. You get way more current. This would be current of 1. This would be current of 2 because of that idea of resistance. So you talk about your slope being the inverse of resistance and then use that to explain how that satisfies your equations. All right, next, starting to do some math now. So in circuit 2, R is 40 ohms. So let me just draw that circuit out over here. You got this amp meter with little r, then you got this big 40 ohm resistor over here. And it says the voltage across it, if we were to tap across that guy right there, the voltage would be 2.5 volts. So the first thing to do is you have a voltage and a resistance, use Ohm's law and solve for the current. If you know the current, then that's going to be the same amount of current going through up here that it is right here. So I have 3 volts in my power supply. I know the voltage and resistance of this single resistor. I'm going to solve for current. When you do that, let's see, your I value, voltage, I don't have a calculator, 2.5 over 40 should be 0.0625. Someone check that for me. I guess I could too, but I'm going to keep talking. If that's wrong, jump in. But 0.0625 amps of current. And if you have 0.0625 amps of current running through there, then this has to be 0.0625 amps. 2.5 cut in half, cut in half. Yeah, I think that's right. All right. So then, if you know the current going through this little guy is 0.0625 amps, we have to think, what would the voltage across this be? Thank you, David. It is correct. All right. So the voltage across this thing is going to be whatever's left over. If I had 3 volts to begin with, and I dropped 2.5 volts over here. Let's try this again. Can you see that? Nope. Oh, that's weird. My pointer only works on a single document. Anyway, if you're going to drop 2.5 volts here, then you're going to have to drop 0.5 volts across this. So I have 0.5 volts equal to 0.0625. Again, use Ohm's law, and you can get that the, oops, I'm going to write it with the lowercase r. You can solve for that resistance as just 0.5 divided by 0.0625. And that, more math. The other one was 1/8, and so half, 8, right? Okay, guys, check me. I don't want to take the time to go get a calculator. So 8 ohms. Oh wait, we have a rubric. Anyway, it should be 8 ohms. Let's say it's 8 ohms. I'll check. Nope, I'll keep talking. You guys check me and then chime in if it's wrong. All right. So if that's an 8 ohm resistor and that's a 40 ohm resistor, this doesn't seem right. 8 ohms. 43 divided by 48. Okay. Anyway, sorry. This is where this format is not ideal for a quick study, but anyway, we'll keep going. Your voltmeter in circuit 2 is replaced by 120 ohm resistor. So now we have, thank you, Nathan, for correcting me. Hey, and I'm sorry, by the way, for spelling your name wrong. I feel like a jerk about that, but I can clearly see it's D-I-E-K and not however I did it. I put the I before the, I don't know. It's a mute point at this time. So we now replace that with 120 ohm resistor. So you have to do your parallel rules here for knocking that down. You'd have 1 over 40 plus 1 over 120 all inverted. Well, that would be the same as taking 1 over, what, 3 120ths? No, 4 120ths. Does that sound logical? 3 120ths plus 1, yeah. 1 over 4 120ths. And so as you're doing that, then you get a value of 30 ohms for that section. Go back. There you go, 30 ohms for that section. And you have a 3-volt power supply still. So if I have the total total resistance there of 30, and I'm supposed to be finding the equivalent resistance, you're just taking that 30 ohms plus the amount that you just solved for over here, which is the 8 ohms, and you're plugging that in to get a total of 38 ohms. Then you want to calculate the current in each of the resistors in parallel. And there's a couple different ways of doing this. The first idea is that you can think of as this, let me show you, this pathway here will draw 3 times more current than this pathway because it's 3 times less resistive. I don't know if that makes sense, but Elizabeth just got here. She's wondering if this will all be archived to watch later. Yes. Maybe I'll take the video, like Google sends me just a full video file. So maybe I'll just dump that on. I don't want to take the time to edit those because I'm making more videos that are taking up my time. So I'll probably just dump the links out on Google Classroom and then you guys can watch the video. The only problem is those video files are huge. So yes, they should be available later, but yeah. I'm going to give you guys a Google survey after this to figure out like what, as I'm like working through this, I'm realizing like what would be like the most efficient use, just to see the scoring guide, to check, or to have me just work it out and stop talking and just work it out all the way from start to finish. Anyway, I'm learning this as we go. So, and making it up as I go. So please give me feedback when you get to that point. All right. Anyway, the current going through each. I think one of the easier ways of doing this is just splitting up and saying this is 3 times more current than the other. And so if you had the total, right, the 3 volts divided by 38 ohms is going to equal the total current. This will be I total. Then you can just take a proportional amount of that total and say this one will have 3 times more than the other. Another way of doing it is once you know that total, you can just take that total multiplied by this resistor here, that resistor of 8 ohms. So let's just figure out what that would be real quick. You got 3 volts divided by 38. That's 0.079 amps. So 0.079 amps. And if you take that 0.079 amps times that resistance of 8, and you get that we have 0.632 volt drop across that little resistor. Well, then you have to drop the rest of the amount, whether I go down this pathway or this pathway. So if you take 3 volts minus 0.632 volts, that'll be left with the voltage across each of those branches. And so you got your 40 ohm and your 120 ohm, and they should each have a voltage of whatever 3 minus 0.632 is? All right, 2.368. So there's let's do a different color, 2.368 volts across each of these. And then you could take that voltage divided by that resistance and solve in that way as well. So either proportional or just get the values and solve it out. And that is how you do that last problem. One more time, let's go back to the scoring rubric just so you can see what they would have given points on. All right, checking our work. You got 1 point for calculating correctly to 30 ohms, another point for adding the value of R from the last part. So let's say on this was the day of the test and you didn't get that first part right. You didn't know that it was 8 ohms. You should at least say, well, I would take that answer plus the original from the last one. And I think they'll give you credit for that. Then in that bottom part, good, we got that, 0.079 amps. Get you 1 point, and then for calculating the currents in each, and those are the values that you should get. So I'm not going to take the time to solve them, but you do get that voltage divided by each, and that should be the currents. So that is it for this. I'm going to switch back to give you guys your homework. I'll post this in Google Classroom too, but